So Miao was a professor of physics and astronomy at UCLA. He is, I think, internationally renowned as a pioneer for the development of different ways of imaging X-rays and electrons, not optical ways, computational ways. He performed the seminal experiment of extending X-ray crystallography to allow structural determination of non-crystalline specimens in 1999, which is known as coherent diffractive imaging, a form of lensless or computational imaging. In 2012, he applied CDI algorithms to pioneer atomic electron tomography and determine the 3D structure of materials without assuming crystallinity. He has performed several groundbreaking experiments to determine the 3D structure of crystal defects in single atom level. In 2019, he developed 4D spectroscopy to observe crystal nucleation at atomic resolution, showing that a theory beyond classical nucleation theory is needed to describe nucleation of the atomic scale. More recently, he has advanced AET, which is tomographic imaging, to solve the long-standing grand challenge of physical science, determine the 3D atomic structure, amorphous solids for the first time. He's had many awards and many honors. He's the Deputy Director of the NSF Center of Science and Technology Center, Associate Editor of Science Advances and Crystal Reviews. He's won a number of awards, including the Outstanding Teacher of the Year Award from UCLA. He's a Fellow of the American Physical Society, the NSF Creativity Award in 2018, and Innovation in Material Characterization Awards in Material Research Society in 2021. His talk is on computational microscopy, CDI, coherent diffractive imaging, with photons and electrons. So it's very great to have you, John.
Okay. Paul, thank you so much for a nice introduction. And there's an echo here. Can anyone hear me well? Can you hear me?
Yes, we can. Thank you.
Okay, good. Thank you. Paul, thank you so much for the invitation and for the very kind introduction. I'm very sorry that I couldn't be there this week because I organized an international workshop at UCLA this week. I visited Paul a few years ago at University of Ottawa, and I really had a great time. I remember Paul showed me through the river and with eyes and the building, and it's really a great time. I hope, yeah, I will visit Ottawa in the future, and I hope Paul can come to visit us there in Los Angeles. So I'm going to talk about computational microscopy, coherent diffractive imaging with photons and electron. So let me just get to the laser point. Oh, it's okay. So it's not moving. Oh, okay, good. Yeah. So I believe there are revolutions in microscopy, imaging, and diffraction. Now, many of you are familiar with, when you high school, you use optical microscope to look at different structures, insects get a magnified image, and you turn the knob, you can change the magnification. But I think now the imaging microscopy is completely different from those kind of optical microscope. It's a resolution from micron to angstroms, super resolution fluorescence microscopy, CDI, 3D X-ray nanoscopy, electron microscopy can atomic resolution, X-ray crystallography can get a sub-angstrom resolution. And also there's time scale from minute to attosecond. And Paul is really a pioneer for this attosecond science. So, atoms and electrons, they move in 3D space and also time. This is why I make this field such an important and exciting direction. The reason I believe there are revolutions because of brilliant X-ray sources such as X-ray flatron lasers, very expensive. Each one costs almost $1 billion. and also advanced synchrotrons and ablation collector electron microscopy, and a powerful imaging method such as super resolution fluorescence microscopy, cryo-electron microscopy, and the CBI. I'm going to mainly today focus on the CBI. And also detector play a very, very important role. I remember a few years ago, the detector really made it important to impact to cryo-EM and our field is originally developed at the CERN, the high energy physics lab. And I found this cross-disciplinary, it's truly important. The detector made a revolution to many different fields in microscopy imaging. And nowadays with single and electron counting, and also advanced algorithms, big data, fast computers, and deep learning. I'm sure everyone heard about deep learning become a very big deal in many different fields. So the reason of I said one of the breakthroughs in the coherent X-ray sources, if you look at Moore's law, 12 orders of magnitude in 6 decades. But the X-ray brilliance, just coherent X-rays, is 20 orders of magnitude in 6 decades. Now, X-rays are bosons, so you can put as many in the same quantum states. So there's basically no fundamental limit. That's just the kind of created this kind of CDIs right now under rapid development because of the coherent sources. Now, I'm from Los Angeles, so if you have a chance to visit LA in the future, there's a very nice place called Huntington Libraries and Gardens near Caltech. And in that place, there's many old books and some beautiful gardens. One of them was written by Robert Hooke. So Robert Hooke built a microscope. He was not the first one built the optical microscope, but he's among the first one. He built a microscope, look at a biological sample in 1670. And he looked at many different biological samples. I was so impressed. There was a book in that place, in the Huntington Library and a garden. A very thick book. He handed you at that time, of course, there's no camera, there's no film. He handed you all the images. And he looked at a piece of cork and he found this, this compartment, and he named this cell. So the terminology cell was first coined by a physicist, Robert Hooke. And since the 17th century, more than 300 years ago, lens-based microscopy has played a very important role to the modern science and technology, right? But there's another way to get the lens actually do the Fourier transform. Fourier transform may keep the magnitude in the phase, but you measure the diffraction pattern, the phase information is lost. In quantum mechanics, we know the phase information cannot be measured. The phase of the wave function cannot be measured. So one of my former students did this very interesting experiment. She took these 2 images and calculated Fourier transform and swapped the phase. And you see, this looks like it's B because the phase information from B, although the magnitude from A. And this looks like A because the phase from A, although the magnitude from B. So our eyes and your eyes are very sensitive, so sensitive to phase. As long as you get a correct phase, even wrong magnitude, you can still recognize the image. But unfortunately, the phase information cannot be directly measured. So in this talk, I'm going to talk about how can I get the phase information back from the diffraction intensity. Okay, let's go back to understand the method we use called oversampling and combine it with iterative algorithm. So to understand oversampling, let's look at X-ray diffraction by crystals. So this is the first X-ray diffraction pattern of a crystal obtained by Max van Looy and his students. And you can see the patterns, very low quality in today's standard. But they actually, this experiment did 2 important implications. One is verified X-ray waves. Second, we can diffraction X-ray from crystals. And 2 years later, actually, Max van Looy got a Nobel Prize. And this is the first experimental atomic structures solved by William and Lawrence Black, father and son, in 1 year later. So after Lowry's experiment, the father and the son did experiment. They actually use the so-called Black's law, solved the atomic structure of 2 crystals, salt and a diamond. Table salt and a diamond. That's the first solved, more than a century old. And so for crystal case, it's well known that if you have this unit cell, let me just get it later. Okay, this is a unit cell, which you have many identical copies. That's 1-dimensional, capital N. And shine X-rays that's equivalent to take a Fourier transform and get absolute value squared. Now we just do absolute value. Okay, so get this kind of discrete peaks, right? You can see a bunch of delta functions, and this is a very Fourier transform just transfer a bunch of delta function in real space to reciprocal space, and this is A, this is 1 over A. There's no information between black peaks, right? Discrete peaks. That's a crystal. Now, there's another very important theory called Shannon sampling theory. In fact, everyone is using Shannon sampling because we use, you send email and you text, that's always a digital signal. But Shannon was an engineer at the Bell Lab in 1949, published a very important paper. And he showed that how to send a digital signal from Ottawa to Los Angeles, send digital signal, right? This is, we can digitize this signal and send it from Ottawa to Los Angeles. So he was thinking how to send, how far we have digitized it in Fourier space. Now, electrical engineering, you get the Fourier transform, you get both magnetic phase. You can either send this signal or you can send this signal, right? And so he showed if this bandwidth limited, right? You send an email, it always says limited. You cannot go forever. And he showed that you just sample 1 over A. And this is called a Nyquist interval. And he's looking back, that's exactly corresponds to the crystal and the black peaks. That's also 1 over. So he showed mathematically that's only, you just need, if bandwidth limited A, you can sample 1 over A. Okay. And now for black sampling, right? The top is the Shannon sampling, there's a magnitude phase, but if there's no phase, then you cannot get this back. Okay, that's right, because the phase information is unknown, so you cannot get this back. So mathematically, one can show if you only sampled at this intensity point, this infinite number of the signals correspond same intensity measurement. And one way to do it, you just use a different phase, combine this intensity measurement to inverse Fourier transform, you get the different signal, right? So it turns out if you can sample finer, intensity finer, smaller than 1 over A, right? And then you can see this, you can distinguish the red one from the blue one. So these correspond to black and the blue, uniquely determine the blue one, and the black and the red uniquely determine red one. So this is oversampling. Actually, in this paper, we showed at what condition this can be, in principle, can be uniquely retrieved from the diffraction intensity. Just so this is a pictorial representation of oversample. Let's say if a biological cell, let's say kind of a cancer cell, if you measure diffraction intensity, right? Now, if you can get the phase information, you can do inverse Fourier transform and get the structure. Now, if you do the same experiment, but this time you use the detector size is the same. Okay, one by 1 inch. That's a 1 by 25 by 25 centimeters. Okay, 25 by 25 millimeters. Let's say this 1 by 1 inch. And but the pixel size here is, let's say 10 by 10 micron. Okay, but here is here is I can make it just like it. So let's say this is 20 by 20 micron pixel size. So it's about 1K by 1K. Now, but here it's 10 micron, 10 by 10 micron. So each pixel here corresponds to 4 pixels here. You sample more information, right? So this array size, it's larger. But because the pixel size, the overall detector size is fixed. The other size I said is about about 1 inch, so about 2.5 centimeters. And the spatial resolution of the image is the same. So if you can get a collector phase information to inverse facet Fourier transform, you get the same spatial resolution as the top. The spatial resolution depended by the diffraction angle and the wavelength, right? We well know diffraction angle. But mathematically, one can show if we can get a collector phase information combined with oversampling diffraction intensity, this region must be 0. Now if you in collector phase, then this region not 0. So actually, in this case, so we use called this. So it turned out in this paper, we showed one independent measured intensity. This kind of independent measured intensity points are larger than the unknown variables inside this small square, right? Because these zeros, we know it. Right? If we can get the collector phase information, okay? So it turns out in this case, basically, if if this region, the low density region, the white region, larger than the inner square, and then the phase information in principle embedded in the diffraction intensity. Now this is not a holography because there's no reference way, no object, and the only diffraction. Right? And then we can use iterative algorithm to recover the phase information. Now, iterative algorithm actually have been developed for years. And so basically we start first, on the computer, we generate a random phase angles. So the advantage is we don't need any model. So random phase angle, combine and measure the magnitude, we get a Fourier transform. And we do inverse factor Fourier transform, we get electron density. So we know that because the phase incorrect, there's some region outside of this white, outside the, in the white region, there should be no density. But because of incorrect phase, those are not zero. So we slowly push close to zero. Okay, this kind of, we don't set them to zero, but slowly push them. Then we get a new structures and do fast Fourier transform to get a new Fourier transform. Every time we just updated the phase. We updated the phase for each iterations. We keep the same measured magnitude. Now, usually after a few hundred iterations, the correct phase can be recovered. So this is an early version, Jim Finnap developed, and based on the Gertrude-Saxton algorithms, but we actually recently one, now many groups develop new algorithms. Ours actually a lot much better than the 1978, the Finnap algorithm. So this is the first experimental demonstration. Actually, was when I was a graduate student. It's called now it's called a coherent diffraction imaging. It's basically unification of diffraction, imaging, and microscopy. So the way I look at it is a microscopy based on Young's double slit experiment. Now you just on the non-crystalline samples and you shine coherent wave, get an interference pattern, and then from the interference pattern we can use if you oversample sufficiently large enough, we can get the phase back. Okay, and this is the first experiment demonstration, and you can see the image. It's turned out to it's a very good reconstruction, very consistent with SEM images. It's made of a bunch of gold dots on the silicon natural memory. The overall size about a few microns. After this experiment demonstration, this field suddenly really become so important. And a few years ago, my collaborators and I wrote a new review articles in Science on a different CBI method. So CBI methods have been broadly applied to physical and biological sciences, use single-tron radiation, X-ray free electron lasers, high harmonic generation, electron and light microscopy. So there are mainly right now three versions. One is the plane wave CBI, the original one that I demonstrated, and the other one called a tachography. Tachography also called a scanning CBI. So every time you overlap the probe with the sample, and then you can measure diffraction patterns. So the advantage is you can study extended objects, and also because you have an overlap, that the redundancy help the phase retrieval. Now, here everything is related to the number of independent equations unknown variables. It's very surprising because this is a non-linear problem, right? The phase information is lost. But turns out just the intensity, you can even almost consider as a linear problem. The measurement and the unknown, as long as larger than a few times larger than the unknown variables, the iterative algorithm not very powerful can recover the phase back. And the third one, the black CBI has become measure black peak and map out the crystal strain. So now I just say a few more words about the tachography. Tachography, basically you scan the probe. This is a probe on the sample. This is a neuron, and you measure diffraction pattern. Okay, every time you overlap with previous position, and it turns out, and then you do the reconstruction, and it becomes a very powerful method. It's not only just an X-rays, electrons, and light microscopy. It's become a very popular method. So in the following, I'm going to show some of our recent results. The first one we developed called in situ CBI for imaging dynamic systems. So tachography, based as I showed, they use a partially overlap region in the space domain as a constraint, right? So basically overlap, you just reduce the number of unknown variables while maintaining the same number of equations. And in situ CBI actually use a partial overlap region in the time domain as a constraint. So what we did is we divide into two regions. One is a static region, dynamic region. Dynamic region can be a biological sample. It changes as a function time. And this is static region. So we measure the diffraction pattern and a sequential of diffraction patterns. And then we use iterative algorithm can get the image back. Now, this is not a holography. The holography case, the resolution is limited by, if it is reference, the size of the reference beam, right? So, but in this case, we can get the resolution is really limited by diffraction pattern. And I'm going to show you some kind of examples. So one is, we captured lead dendrite growth on electrodes during the battery cycling. This is in the liquid, and you can see we apply different voltage. You can see dendrites growing, and we can capture this dynamic process. So we have another. I didn't show this static region here, but static region turns out a very powerful constraint to help reconstruct dynamic. And then if we do tychography scanning as a function of position, and then there's some blurred because there's a dynamic phenomenon. So this actually you can see. So tychography is spatially scanning CBI. This in situ CBI is a temporal scanning CBI. That's one way to look at it. And then we also tried biological samples. This look at the cancer cell to cancer cell fusion, and then the kind of a dye. This is all in the liquid. So we are trying to, here we did actually just a laser experiment. We can in principle apply these techniques to X-rays to get very high resolution images. And I also want to talk about something actually related to the attosecond science. So as I mentioned, Paul is really a pioneer of this field, and this is a very nice review articles about attosecond science. Now, so far, the attosecond science mainly using spectroscopy. I think there's a reason. The reason because the bandwidth is very broad. This is later uncertain principle, right? Delta E times delta T is larger than H bar over 2. So if 1 attosecond, this broad, the bandwidth is very, very large. The delta E times delta T is larger than 1800. So to date, attosecond physics has been primarily performed with spectroscopy. Now, I believe if we can imagine that, we will provide a much more structured information. But the broad band, it's a problem because the bandwidth, in this case, going up 100%. Like the white light, our eyes, it's about 50%. So this is even larger than the white light. Now, but turns out using this tychography CBI, it's a very powerful method. Now, we tried we did this simulation, and we simulated this attosecond pulses, okay, with the delta E over E about 100%. And then we scan these attosecond pulses with a sample. We first try to test the sample. And you can see this interference pattern is kind of, there's no speckle because of the bandwidth is so broad. They are all blurred. But it turns out if we can have a large enough overlap and the algorithms are powerful enough, can reconstruct images at different wavelengths as well as the spectrum. So here I'm going to show you some simulations and some experiment that we just did at the LED. So first simulation, we just the same test the samples, and this is one of the diffraction pattern. You can see there's a very fuzzy diffraction pattern because of the bandwidth so large. And then from measured diffraction patterns, we can reconstruct the spectrum. The true spectrum corresponds red. The greens are recovered spectrum. And then here we simulated two structures with actual absorption edge. And we can do the same thing, and we can reconstruct. Actually, there's indeed the absorption edge. We can see the contrast change at different wavelengths. And then we did LED experiment. So this corresponds to the measured, the red corresponds to the measured spectrum, and the green is the recovered spectrum. So overall, I mean, the algorithms turn out to be very, very powerful. So here shows, I just first show the simulation. We actually reconstructed 17 different wavelengths. So here I just show three of them. This is the original image at the different wavelengths. You can see the shorter wavelengths. We use a pinhole to define the illumination area. So the resolution getting larger when the small wavelength. So this is a reconstructed region. You can see the field of view here is larger, but the resolution here is a shorter wavelength larger. And we can reconstruct as well the probe. This is a probe at different wavelengths. This is 3 of the 17. And here it shows the element specific image reconstruction at the 70 different wavelengths. And we simulated actually in this case 10 nanometer aluminum and 100 nanometer thick aluminum and then 100 nanometer boron. So boron absorption edge is 6.6 nanometers. This is CBI is a boron. So now at the beginning, there's no contrast below the absorption edge. Then above 6.6 nanometers, the boron edge, then you can see sharp images. So total, if we counted the 17 images, the resolution is getting larger because we getting shorter and shorter wavelength. So we can, again, we reconstructed the spectrum, the probe, 17 probes, as well as the images. And then we did experiment is it's LED. We use the LED. We also get 17 reconstructed probes. These probes, there's 3 of them, and 17 image reconstructed images, and this the reconstructed spectrums. So overall, actually, the very good agreement. All the different 17 mode, all show good reconstruction. So now we are looking for actually some use attosecond pulses to do the experiment. I think it is, if it works, it would be great. So that's kind of the experiment I showed potentially to combine attosecond pulse with CBI. So in the following, I want to talk about some work that actually we haven't published yet, actually related 2D and 3D topological spin textures. Many of you heard about the topological materials, right? For this is skyrmion magnetic materials. The 2D topological spin textures we call the neo-type skyrmion, is the Brock-type skyrmions, and there are these 2 types of skyrmions. And there's also 3D topological spin textures. This is called topological magnetic monopoles. Now, this is not a different from the magnetic monopole in the fundamental science, like in electrodynamics. This topological magnetic actually has to be observed. But in this case, we're going to show we actually develop a method to look at their interactions. So this one, it's M as a magnetization field, and this emergent B field. And here I think Q, the topological charge +1, this -1. The topological magnetic monopole can create, annihilate, or manipulate 2D skyrmions. However, experimental evidence of this 3D topological spin texture has been largely indirect or qualitative to date. And there's indirect evidence to see it, but not truly see it, you have to get a 3D. So over the years, actually, last year, we developed called a 3D soft X-ray vector tachography. And we did an experiment at the Advanced Light Source at the Lawrence Berkeley National Lab with 2 circular polarization, left and the right. One left, one right. It's energy around 856 eV. And then we shine this beam on a matter lattice. Why called a matter lattice? We created this kind of a 3D structures. This is called a matter atom. Each matter atom is made of amorphous silica, about 60 nanometer in diameter. And between them, we infiltrated with nickel. This is nickel, the magnetic materials. So this created geometrical frustration. And we try to look at these magnetic structures. At the beginning, we didn't expect to see topological magnetic monopole, but we actually did it up from our reconstruction. We did a quantitative analysis. We found that there's quite a few there. And the reason that we can get a magnetic structure is because of the different polarization, the spin have different contrast. Now the challenge here, we want to get a 3D. These are different from conventional tomography. Tomography is a scalar reconstruction, but this is a vector. We need a lot of data. We have to use different tilde axes to get many projections. We actually get 6 projections. We get almost a few terabytes data. And again, here in the following, I'm going to show you the movie. First, we get a 3D scalar reconstruction, and then we get the 3D vector, the magnetization vector field. And we can zoom in. You can see there's a magnetization field only in the nickel region. Okay, there's no in the silica region. There's no magnetic vector field. And then we're going to zoom in to see actually this a pair of topological magnetic monopole, one positive and negative. The red corresponds to positive and it's negative. The line correspond magnetic field lines. And then we're going to go to 2 positive and 2 negative pair. So we're going to go to 2 positive pair. Okay, I can see the this M field, magnetization field, actually kind of points outward, and this magnetic field lines, and then we can go to two negative pair, and you can see in this region there are two negative pair. The kind of the magnetization field points inward. So we did actually a quantitative analysis. All these calculations can be done automatically because the advantage of this topological charge is preserved. So we found there's 68 topological monopole plus and 70 minus. This corresponds to different dots inside of this topological magnetic monopoles. And then we can look at individual ones. This is one of them in the octahedron region. So this H sphere corresponds to the amorphous silicon, 60 nanometer in diameter. Inside of one, there's topological magnetic monopoles. Now here shows magnetization field, and here's the tetrahedron side. This one corresponds negative topological monopoles. You can see the M field, magnetization field is points more inward. And because we have about 140 magnetic topological magnetic monopoles, so we can do statistical analysis. We can look at the distance. And turns out in this case, the average distance about 18 nanometers between positive and negative. And between the positive is about 36 nanometers and negative about 43. Now this actually, when we did it, this all automatically calculated by a code. The code can calculate the topological charge, do the integral calculate charge. And we didn't expect to know what we will see. And it turns out that this actually the distance positive plus minus shorter than positive negative. And this is consistent with theory. I mean, you can see this is kind of a attractive, this is repulsive, right? So this actually work shows, really this density image method or CBI method combined with polarization for the photons, so we can really look at about magnetic structures at a very high resolution. The resolution is about 10 nanometers, only limited by the signal, the diffraction angle. So in the following, as Paul mentioned, I want to talk about something I thought is very, very interesting. We see the determine the solidity atomic structure of amorphous solid. Now I understand that this is a photonic symposium, but I just want to show here, this is a photonic method that being applied for different fields that can make a bigger impact. This one I really feel, personally, that's my personal experience, because we do a lot of optimization problems. So we try to solve the phase, use optimization. We try to find a global minimum. So my experience, human nature, one of the kind of human nature is we always to be comfortable. I want to be comfortable. That we don't like to be uncomfortable. But for science, it turns out I find it's very beneficial, comfortable with uncomfortable. This is why I applied some of the photonic method, like a CBI method, to different fields and make a bigger impact. So we apply the CBI method to develop atomic electron tomography. So here we use iterative algorithms. The algorithm is not to solve the phase problem, but try to get from a limited number of the measurements and noise, incomplete data, try to get the best possible reconstruction. So this is all based on iterative algorithm, turned out to be very, very powerful. And now there's actually machine learning become, hope maybe in the future, machine learning will replace the iterative algorithms. So over the years, we really solved some important problems. As Paul mentioned in the introduction, we see the nucleation, classical nucleation theory breaks down at the atomic level. But here in the point, I'm going to really talk about amorphous material. Here, just kind of an introduction. Okay, why this 3D structure determination of crystal so important? The first experiment, just atomic structure mentioned, the Bragg's father and the son in 1913, table salt and a diamond. Okay, this is now in the high school textbook. And also, now this is kind of a, you can see each one different, the iron corresponds to the FCC structure, the face-centered cubic structure. It turns out the FCC and HCP, hexagonal closed packet, this corresponds to the highest density packing. First conjectured by Kepler, the famous astronomer, the 17th century. So he conjectured that FCC face the center of the cubic and a hexagonal closed pack. This graphene is the HCP kind of stuff. Have the highest density packing, okay, about 74%. Basically, you can fill in space. Now, there was a mathematical proof in 1998 by Hills, and he used computation plus the mathematical theory that proved it. So what is the FCC? FCC, you just assume you have a balls, okay? All the balls same size. You pack the first layer, you put it them one to next each other, and they form this two-dimensional hexagonal packing. Right? And then you put a ball on the top, right? Between the top of the intersection, three balls, you put one, like a B here, right? And a B, so the second layer is same. And then the third layer, you have two positions. One is A, which means same as the first layer. The second option is a C. You put it between this three neighboring ball. You can either between these three ball or three. So this is called FCC, face the center cubic, ABC, ABC. You just keep it. And this is AB, HCP, hexagonal closed pack. And also, this has been applied to the biological samples, the double helix, that's based on Franklin's diffraction pattern, is a crystal. And this is the first atomic model of a protein by John Kendrick. All this made a big impact, for crystal structures. Now, it well established that liquids and solids are two fundamental states of matter. Although liquid and amorphous solid are more ubiquitous in our daily lives than crystalline solids. And you think about the glass, our body is not amorphous. The liquid is water is not a crystal. So the amorphous materials are more ubiquitous in nature than crystalline solids. But due to the lack of long-range orders, there are 3D atomic structures that have defined direct experimental determination for more than a century. Because if you are amorphous, you don't get a discrete diffraction pattern. Right? Everything kind of become rings. How can you get atomic structures from this diffraction pattern with rings, concentric rings? And now in 1952, Frank, a British physicist, hypothesized that icosahedrant order is the prevalent atomic motif in monatomic liquid. Okay, he published the paper, theoretical papers, which has been widely accepted in the community. And also in 1995, Philip Anderson, the very famous condensed matter theoretician, wrote in Science the deepest and most interesting unsolved problem in solid state theory is probably the theory of nature of glass and glass transition. And because the experiment is very difficult to measure. So here I want to show icosahedron. Icosahedron is one atom in the center and 12 surrounding. Okay, they form this 12 5-folded vertices. Okay, each one is 5-folded symmetry. And you can see this icosahedron. Okay. Now, it turns out icosahedron is the highest symmetry in nature. Now, a lot of violets have this icosahedron order. As I mentioned in the previous slide, FCC, HCP, this density packing for long-range order. So for crystals, FCC, HCP is the most efficient packing, density packing. That's for globally. But for locally, it turns out FCC and HCP not the density packing. This icosahedron is the density packing. If we're given certain atom, so the density packing is this way. Now you may ask why nature just use icosahedron. Turns out icosahedron cannot fill in the 3D space because this is a 5-fold symmetry. You cannot fill in the 3D space. Now there's also quasi-crystals, and some special cases you can fill in. These are quasi-crystals. Okay, so here shows the icosahedron will rotate this 12 5-fold vortices. But I can also call your attention that this is called a pentagonal bipyramid. One atom top, one atom bottom, and 5 atoms surrounding. Okay, so each icosahedron has basically have a 12 pentagonal bipyramid because one atom here, one atom here, you can form the icosahedron. So you have a 12 vortices. They form actually 12 pentagonal bipyramid. Turns out now I'm going to show this is why it's important in our observation, in our experimental observation. So we did this. This amorphous nanoparticles made of palladium. There's some actually different color that's correspond to nuclear, but more than 80% are amorphous. And it turns out that those kind of atom arrangement is not random. There's some nature actually not prefer random. There's some order. So I'm going to show you what kind of order in this amorphous material. We started a few different amorphous materials and made by different methods. This one made by physical vapor deposition, a thin film, a portion of the thin film. If you take a Fourier transform or measure diffraction pattern, it's like amorphous. And this one is made by a completely different group. It's a chemical method. There are more atoms, more than 52,000 atoms. And if you look at pair distribution function just the atom and the neighboring atom, okay, the pair. This is called the first peak atom and the second neighboring atom, the second peak. So they kind of amorphous. And then we first did we got a short range order. Short range order, we got the Voronoi index. There's a war in the Ukraine, and Georgy Voronoi was a very famous Ukrainian mathematician. So he developed this Voronoi index. It's a mathematical tool to find the atom and the neighboring atom, the short range orders. So we use 4 numbers to represent each Voronoi index. So the first one corresponds to symmetry in the 3-order symmetry, 4-order symmetry, 5-order symmetry, or 6-order symmetry. Okay. So in this case, for example, there's 0 3-order symmetry, 2 4-order symmetry, 8 5-order symmetry, 2 6-order symmetry, right? So for crystal, actually, it should be most like this, but it turns out this is amorphous. You can see our samples, although different, made by different groups, they're consistent. And then we look at how this atom actually packed in these amorphous materials. They form this, we found they form triplet. Okay, the atom, this atom, 4 atoms surrounding this top, bottom, and this 4 actually is connected, so 4 atoms and top, bottom, and this is pentagonal bipyramid, as I showed, the top, bottom, and 5 surrounding, and this hexagonal bipyramid. Okay, and then for each one corresponds. This 4 atoms form this tetrahedron, right? So each tetrahedron we find the centroid, center of the mass, the black dot. So we connected these 5 black dots together. We form this represent the pentagonal bipyramid. Okay, so each dot is not a one atom, but a centroid, center of the mass of 4 atoms. And we find 5-order symmetry is most abundant. Now this is kind of it's expected, right? It should be a lot of 5-order symmetry because 5-order symmetry icosahedrons locally is the highest packing density than FCC and HCP, right? And then, but what we found is that instead of they form icosahedron, this amorphous atoms form this called a pentagonal bipyramid network. Like they share as I mentioned, each one the pentagon represent a pentagonal bipyramid. Okay, 7 atoms. So each pentagon they share edge. We found the most abundant, the most actually they share edge. Share edge means in this actually they share 5 atoms. Okay, now there's one pentagonal bipyramid, it's top and bottom, 1 2 3 4 5, and the same as other ones, they share edge. And they form this edge and form these networks. So pentagonal bipyramid, they form edges instead of form icosahedron. So the icosahedron needed 12 to form one icosahedron, right? So this we found only partial icosahedron, only n equal to 8, n equal to 3, n equal to 5, n equal to 5, n equal to 3. So it's a very interesting nature. And it makes sense. The pentagonal bipyramid turns out to be the more fundamental than icosahedron. And in our experimental data, there's no almost no very small. Have a 12 12 means just call it the icosahedron, right? And this corresponds to the largest medial range order. We call it the medial range order inside this amorphous material. This actually, in all these amorphous materials we observe, and the distance about more than 2 nanometers. So this is nobody even have observed it before. Of course, it is very difficult to study with other methods. And the only way now we can identify the individual atom, locate the position of the atom with high accuracy. This allows us to identify this pentagonal bipyramid. So this is kind of a new type of the MR. And so here, so far I showed this monoatomic amorphous material. So we also started multi-component metallic glasses. So the multi-component metallic glasses, they are so-called efficient cluster packing model for metallic glasses, but there's a debate. So the debate between these two papers, one is published in Nature Materials 2004, the other one 2006 in Nature. So here, the model is based on, okay, you have a solute, atoms, and a solvent. Okay, this is a solute, the blue solute, and a solvent surrounding. They form the clusters, the short range order. And then this is short range, each atom clusters, according to this Dan Milikos paper, these clusters form this kind of FCC and SHCP-like MRO, medium range order. So in structure, there's a short range order, medium range order, long range order. Crystal corresponds long range order. Amorphous solid don't have a long range order. The short range order, medium range order, right? So here, he proposed this form, this called FCC, HCP-like, crystal-like. And then this paper showed the claim based on simulation. These clusters should form icosahedral symmetry. Okay, this form icosahedral. Here's a cluster form this kind of crystal-like, short range or medium range order. This is about icosahedral-like. So we look at samples made of 8 different elements, and now our technique is sensitive to the atomic number Z. Some of the Z is very, very close. So we divided them into 3 groups: type 1, type 2, and 3. So type 3 is red, type 1 is green, and blue is type 2. And I'm going to show you the movie of the this reconstruction. So we go through this. Now, as I mentioned, we can identify the coordinates with a precision about 20 picometers. So 1 picometer 10 to minus 12 meters. So very accurate. And you can see that compared to other types, so red, type 3, more uniformly distributed inside these samples. This turns out the red corresponds to solute, and the other 2 types called solvent. And also you can see some crystal features, the nuclei. Okay, there's some crystal features here. But overall, most atoms are amorphous. And again, this amorphous is not a kind of randomly distributed. We found this kind of the experimental projection. So we take a Fourier transform and gonna get, or we measure the diffraction pattern is kind of a ring, right? And then this from 3D reconstruction, we can see different atoms, different contrast. You can see the blob, the white correspond type 3 atoms. They're more uniformly distributed. From the atomic coordinates, we can calculate the pair distribution function. You can see these are amorphous. And then we also use the local bond orientation order. And you can see most atoms deviate, very deviate from body-centered cubic, hexagonal closed packed, or face-centered cubic. It's like amorphous. And one thing is very interesting for pair distribution function. The pair distribution function is the atom and neighboring atoms. Always, usually, the first peak always higher than other peak. Okay, because you always have the probability for an atom and neighboring atom always larger than the others. But it turns out type 3 atoms, these are the red atoms in the previous video. You can see the second peak is larger than first peak. Means this atom more spread, more uniformly spread. Right? Atom and the second neighboring atom are more abundant than atom and the neighboring one. So we also did this Voronoi index, and this we showed the most abundant to the top 10 Voronoi indices. Okay, this is the most abundant 0.443. Okay, the crystal should be most crystal should be 0.444. And here shows some example of the short range orders. For example, 0, 0, 12, 0 means the 12 5-fold symmetries, icosahedron. This is icosahedron, right? And we found there are 44% of 5-edged faces because we added all the 5-fold symmetry here. So all the corresponds to pentagonal bipyramid, right? That's 44% in this SR, but only 7% of all Voronoi polyhedron are icosahedral. So which means most of them, again, completely different samples, they don't form this icosahedral, but instead form pentagonal bipyramid, and they connect each other from this network. And then we look at how these atomic clusters, packed together. We found the sharing 1 atom, this cluster, this red, the solute atoms, and solvent surrounding. Share 1 atom, share 2 atoms, share 3 atoms, 4, 5. The most actually, the percentage is sharing 2 or 3 atoms. And this atom, this shear actually will form. Then we did the algorithm actually automatically try to search, find what's kind of the medium range order in this multi-component metallic glasses. And we found that they have formed the FCC-like. Remember, this FCC we call it like, it's a translation order, but no orientation order. Crystal has both translation and orientation order. So this is, it's a atomic cluster have no orientation order. And we only show the solid, the center atoms. You can see this from this FCC-like, the 100 direction, 110 direction, 111, this is 111 direction. And this hexagonal closed pack-like, okay? It's a body center cubic-like, and this a simple cubic. So it turns out we didn't see any icosahedral-like MRO. And we found this 4 type of crystal-like MROs coexisted inside of these nanoparticles. And which means that there's some MROs, not only just FCC and HSP, there's also BCC and simple cubic, and no icosahedral-like MROs observed in the sample. So our work confirmed, actually, it seems like this sample is consistent with Miliko's work. And here shows the percentage of this FCC and HCP more abundant than the BCC and simple cubic-like. Okay, so I try to summarize my talk. So since the first experiment demonstration in 1999, CBI methods have been applied to imaging a wide range of samples in the physical and biological sciences. And it's really going in many different fields. It's not only just X-ray, but also high harmonic generation, light microscopy, electron microscopy. And we developed in situ CBI and broadband CBI to probe dynamic phenomena with high spatial temporal resolution and to reconstruct spectra, structures, and illumination probes at different wavelengths. We also developed a solid soft X-ray vector pyrography to directly observe topological magnetic monopoles and probe their interactions. We applied the CBI algorithms to solve central order problems, determine the solidity, atomic structure, amorphous materials. So now with some more brilliant X-ray sources like XFEL, diffraction limiter ring, high harmonic generation, coherent electron sources, I think the CBI AT in the next decade will surely be more exciting than the past one. Finally, I want to thank all my collaborators and my group members, and I have some wonderful collaborators from different sources, and my funding. And also, I want to emphasize, we put our software and the data on this website. So everything, when we publish a major paper, we'll put everything online, and we try to be as transparent as possible. Okay, thank you for your time.